Hello all. My name is Aleena Thomas and I am a master's student at Saarland University. Today, I am going to present this paper that was done as part of my thesis. So let's get started. The research problem that we are exploring in this work is a reduction of unintended memorization in machine learning models with a particular focus on those trained with pre-trained word embeddings. And the tool that we use in order to achieve this is differential privacy. Let us briefly look at the motivation. Speaking of a general attack model, let's say we have a dataset containing mails sent by users, and we are using this to train a next word prediction system. Assume that one of the users has included a sentence with his credit card number. An attacker having black box access to the system can query prefixes like my credit card number is blank, and it would be problematic if the system has memorized the exact number and spits it out during inference. The first question we need to find answer to is how to measure memorization. What we are looking for is a function x which takes in a pre-trained word embedding and returns the measure of memorization that can occur because of using it. But to the best of our knowledge, such a function do not exist. So what we do is to define our own function x. The basic idea is that we use a language model trained using the word embeddings as input features, and then use a metric to estimate the memorization in the final model. In our case, we use a metric called exposure metric. The exposure metric we use in this work was introduced by Nicolas Carlini and the rest. This metric gives an estimate of the model's potential for unintended memorization of rare sequences found in the training data that is irrelevant to the learning task. This metric is what we use to estimate the memorization in our language models. Let us look at this metric briefly. The main intuition behind the exposure metric introduced by Carlini is that they estimate the memorization in a model by comparing the ranking of sequences present in the training dataset against those that were not present. The formula for calculating the metric is given below. Let us look at a simple example to understand how exposure is calculated. Assume that a text generation model is trained with the pin number as 4 threes. Just because the model has seen 4 threes while training, the model should not associate a higher probability to that pin number among all the other pin numbers that the person could have had. In this case, assume that the model ranks the sequence as 10th. And if we plug it into the formula, we get a high value of exposure. In order to study the nature of memorization in pre-trained word embeddings, we use the following architecture. First, we augment the dataset with the secret information and then use the pre-trained word embedding to get word vectors. Finally, we train a language model using a single layer LSTM. Lastly, the exposure of the inserted information in the dataset is calculated on the trained language model. And this is used as an estimate of the memorization of the pre-trained word embedding when used with language models. We have used different settings in our experiment to analyze the exact nature of memorization. We experiment with two types of secrets, a short one consisting of a single word disease and a longer secret type in which we test how well can a model memorize a 4-digit PIN. We have also used two types of datasets for training. One is augmented with a single sentence whose exposure we are calculating, and the other will have additional sentences aiming to confuse the model. We have used 3 pre-trained embedding types for our experiments. In order to see if embedding dimensions affect memorization, we also include 2 variants of glove and 2 variants of bird with different dimensions. These are the exposure values we got for the different word embeddings trained by inserting different secret types into the dataset. On the y-axis, we have exposure, and on the x-axis, we have the embedding types. Looking at the plots, we can observe that all the embeddings show some extent of memorization. As the embedding dimension increases, the exposure value increases with it if not already maximum. We also observe that multiple insertion of secrets confuse the model, and except in one case, all of them show that multiple insertion decreases exposure. Similarly, these plots show the exposure at different stages of training. In particular, we compare glove and randomly initialized embedding in the first plot and glove with BERT embeddings in the second plot. What we can observe here is that glove reaches the maximum exposure value faster than random embeddings. And for the case of BERT and glove, BERT reaches the maximum exposure only at later stages of training as compared to glove. So to summarize, what we have empirically seen is that the embedding type, dimension, and the insertion types have an effect on the memorization in pre-trained word embeddings. Coming to the second part of our experiment, the aim is to use differentially private training in order to reduce the exposure. In our experiment, what we do is to replace LSTM with LSTM-DP. That is, we replace the downstream task of language modeling with the differentially private version of the language model. Now, what is DP? In simple words, let's say we performed an algorithm A on a data set and got result 1. Now, we create an adjacent data set by adding John's data, and we do the same thing to get result 2. If the algorithm A is differentially private, the two results must be similar. That is, looking at the result, a person will not be able to tell if John's data was included in the training dataset or not. Statistics about a dataset can sometimes leak information about the individual records used to compute it. Differential privacy is a mathematical definition of privacy which addresses this issue. It parameterizes the privacy laws incurred on each access to the data. Here is the formula for epsilon differential privacy. The main aspects to consider in differentially private training is noise calibration, gradient clipping, and adding noise to the clipped gradients. We also need to keep track of the privacy laws incurred at each access to the data. These have already been addressed in previous works, and we have used a package called AutoDP for the same. One of the challenges we faced while training is that differentially private training is very slow. For our experiment setup, the training was slowed down by a factor of 60. But this issue was recently addressed in the PyTorch TP package, which was released by Facebook, and it provides an API for faster training of differentially private algorithms. This table shows the results of exposure on language models trained with and without differential privacy. With our differentially private approach, that is called LSTM-DP, we can see consistently improved results. Hence, this approach is successful in reducing memorization. One of our future plans was to try another approach of introducing differential privacy. That is, instead of having LSTM-DP, we have embedding DP. That is, use differentially private variants of the embeddings to see if this is better at reducing memorization. We have already tested this for glove and BERT embeddings, and this method was found to give better empirical results. The other aspect is utility testing of the differentially private versions of models on NLU tasks like text classification and next word prediction. This remains a future work. Thank you for listening. Please do have a look at the remaining slides to see related works. Hope you find our paper interesting. Thank you.